Hello, and welcome back to our CSCI for 30 operating system. And today we will continue our topic related to process and just have quick review because we stop by related to the process we including different type of table. So when we look into the OS control table, including like the memories, devices, file, and process, and when each of these, they also have contains their different type of tables. Okay. So for memory, we do have a memory table, IO tables, file tables, and for the process, so we know we have a primary process table, and each primary table also contains process image. So all these process image will be included right here. Some elements like user data, user programs. That's what we mentioned before. Let's say the program code. Also, we do have the stack heap. Okay, so these are dynamically allocated location for the hold the modified data. Also, we have the PCB process control blocks. And that's the data needed by the OS to control the process. And there's a overall, and also we went through all the attributes. We talk about the process identification, state information, control information. So just like quickly review what we have, including the state right here, some visible registers. Also, we have the control status register, like the PC and a condition code. And for the control information, including the scheduling, let's say we need to know the status. Okay, scheduling related information. Okay, some certain events structure. So far will be the process attributes included. And when we move on, continues related to the process identification. So each process assign a unique numeric identifier. So that one will be the PID process ID. Otherwise, there might be a mapping that allow the OS to locate the appropriate table based on the process identifier. If you know the reason we need to have a table or mapping, because we know we have the main memory. Okay, so all the process located, and then we will maybe have a virtual memory. Okay, we'll swap in out from the second storage. So all these like from the virtual memory. So here's the reason. Also, many of the table controlled by the OS may use process identifier to cross reference the process tables. Okay, these are things. And when we talk about memory table, because if you remember, so maybe like organized to provide a map of a main memory with identification of which like process is assigned to each region. Because you know on the memory, actually they are kind of like not loaded in sequential order. Okay, so maybe they're assigned in different region of main memory. Okay, so this one kind of similar will appear in IO and file table. Okay, so that's why we go through those like the file tables. Okay, all those are existing files, IO table, manage the IO devices, channels, memory table, like we keep track both main and secondary. Okay. And when those processes they communicate with one another, then the process identifier infos the OS. Okay, the destination of a particular communication. So like which process communicate to which one, or the process they are allowed to create other process. Okay, later maybe I can show you some source code like how can we create from a parent create some child process. So identifier will indicate the parent and the descendant of each process. I think this is a pretty common example we're going to use. Is like what's the parent process, and then we can create some like child process. Okay, and then we will try to show like display what's their ID, their PID. Okay, later I will share the source code. So you can take a look of it. And also we have the processor state information. So it consists of the contents of processor register. Okay. Later, you will hear a lot of different type of processor registers, and when we touch or like learn machine language, actually you will see, okay. And well, those like process in one next stage, if you remember, we have the five stage, okay. And also if we including some type of the we have the waiting like block stage, and then sometimes we have suspended more than that. Of course, current information they are all also like is in the register. So when process context switch out, then we must save this information to main memory to freeze. Okay, so we know that we have the freeze of the current stage of process. That's why we need to check the process state information. Here I'm giving you an example, like it's a it's a 86, that means a 32-bit okay system. It's a E flag register. So right here we always like come with for the 32-bit. So we start from the rightmost 0-bit, okay, right here to 32. So it's total 32 bits, right? And we do have an identification flag ID right here. So we have the virtual interrupt pending, and we have the VIF virtual interrupt flag, okay, and then also the alignment check VC, and VM virtual 86 mode, and then we have resume flag right here. So it's from the bit location 16 to 21, okay, and then we have the IO privilege level and the overflow flag. Okay, and also we have diversion flag, interrupt enable flag, prep flag, assign flag, seal flag, auxiliary curry flag, and then party flag and the curry flag. So all different this flag will come with the registers. Okay, so if you remember when you learning maybe C purpose, if you try to adding two large number together, do we have an overflow, or like we have, if adding together we have a carry for like carry one digit, okay, so all this, okay, or that one is like if you declare maybe in Java, okay, maybe simple, if we need to declare some variable like with sign integer like variable, like then we do have a cipher, so right here. And we have more like, let's say Pentium, okay, long time ago. Just quickly go through because it's pretty like old um using for the flag. So you just have a kind of like knowing their categories, including like for the control bit. So you will see the ACID, RF, okay, IOPL, DF, IF, and then TF, the traffic. Right here, they belongs to control bits. Okay, so because you see in this part, and then we have the operating mode bit, including the nested task flag. So you didn't see, so it's a anti, and you have the VM, we have VIP, VIF, so you can see some of right here, okay. So it's the operating and then conditional code. All these are more related to when we do some like mathematical calculation, arithmetic or logical operation. So AF, CF, okay, and OF, PF, SF, ZF, okay. So already right here belongs to the condition code. So just I need to know their categories would be fine. So they belongs to, you don't have to memorize all this. Okay, just have a rough idea. And also there's some like typical elements of a process PCB. And when we talk about PCB, so we need to know including the scheduling and state information. This one actually we extract this part from our previous right here, the business control information like from the attributes, process attributes. Just like quick review of it, because it's exactly same information, because like when we need the PCB for the OS, so we need to know their stage and their priority scheduling event is for our later for the task process scheduling algorithm. Okay, this is a usage. Then we need to tell the data structure. So it's a link to other processes in a queue or ring. Also, there are some like inter-process communication, those like flags and also signals, okay, message. Also, we do contain like some like process privilege. So what kind of privilege they grant in terms of the memory. Okay, also we do have a memory management. Okay, so it may include the pointers to the segments or paging. So this one You just need to know we do have a memory management, but we will talk about segmentation and paging later. Okay, just need to know. We will cover this part later. Okay, and just like reminding what is the role of the PCB. Okay, why it's so important, because we talk about PCB and what's the reason why we need to use it, because it contains all the information about a process that's then need by the OS. So we go through here, like because we talk about different types, scheduling, memory, all these different privilege. Okay, so also it's a block they are read or they can be modified by the virtually every modules in the OS. So it also defines the stage of OS. So right here, different stage, right? Okay, so here's the data. So the difficulty is not access, but it's like protection. Because if a bug in a single routine can damage the process control block, the PCB could be destroyed by the system ability to manage the affected process. Also, a design change in the structure or semantics of the process control block can affect a number of modules in OS. So here's the reason, because if we have the dialog or a boot screen, here's one of the possible reasons, because the damage or change of the PCB. Okay. Just a quick revision. So when you look at the image element, so contains of the collection attribute need by the OS to control particular process that was encoded, and also the state information needed to save by the OS for process when we switch, including all but for the following. So you can like reviewing based on what we go through. So you can go back to the process image, that part, and then actually is because pretty straightforward. So all these elements right here, so you can match, right? So the answer will be pretty straightforward. So you can see what is exceeded. So right here for the control particular process. Okay. So you can see it. And next we will move on to the control and execution of process. So we need to understand some of the requirements and issues need to successfully like support the process by the OS. Okay, so how can we exactly like control and execution of process? Okay, so let's go and move on and check. So the mode of execution, we include like two different types. So remember, we do have two mode. One is called the user mode, and another one is the system mode. Okay, so what's the differences between them? First one, for user mode, it is the lower it's a less privilege, so it's more lower, okay, privilege, and the system mode is more privilege mode, okay. And also user programs typically execute in this mode. Okay, if we do have some user program, then it's in this mode. Okay, if we do have some system mode, so maybe refer to as the like control mode or kernel mode, kernel of the operating system. If you remember in our previous lecture, we talked about like the kernel is like kind of like between, is a we can kind of like say it's a bridge between the applications upper level and then the hardware. So it's a kernel, so it's of the OS. So this one belongs to the system. Okay. And typically right here is there's some function of the OS like kernel, including the process management. So one is the creation, termination of process, and scheduling, dispatching. And if you remember, we have the dispatcher when we talk about a different process, when we need to in different stage, and then we have the dispatch. So right here, and then process switching. Okay, also it's related to kind of similar to the scheduling. Also, process synchronization support the inter-process communication. There's inside the PCB, we do have the inter-process communication, and also management of the control block. So it's a process control block right here, PCB. Okay, and then we have the memory management. Later you'll learn like once the allocation of address space to process, and of course scrapping of page and segmentation management. So later well, that's what we learn. Okay, that's for memory management. Also we have the I/O. We talk about buffer management. That's what we mentioned about this part. This one is the I/O for inputs. Okay, and allocation of I/O channels and devices to process, like this one in the first part of this chapter. So it's like talk about our channels like here. And if you remember, we do have some interrupt handling, right? So they are supporting function, including the interrupt, accounting, monitoring. So all this will be the support function. They're provided by the OS kernel. If you remember, we talked about the process switching. So what's the process switching? Is that it may occur anytime the OS has gained control from the current running process. Okay, some possible events giving the OS control. Let's say they have an interrupt. Okay, we need to react to an asynchronous event. Okay, there's some like external event required. Then we do have a different type of interrupt. Okay, and we have traps. Okay, so those traps, maybe we need to handling of an error of or some like exception condition. If you remember, like we need to like handle some different type of error. Then how can we handle this one? So these are events called trap. And also we have a supervisor call. So we need to call to an OS function. So if we remember some like other functions, then we need the OS function to call those, then we will call supervised call. So these are all the process switching. Then when we need to switch the process, we have one is called interrupt, right? So these are lots of some like sort of events. They are external and independent of the current running process, including maybe we have the cloud interrupt. Okay, this one based on the time, or the IO interrupt, or some memory fault, maybe the location, or sometimes like when we access, okay, we don't have a like maybe sometimes the force of the memory location, including maybe misassign, or like when we mapping, all this is possible. And also we have one is called the time slice. Okay, so the maximum amount of time that the process can execute before being interrupted. So here's one for the time slice. And then the next one, if you remember the trap, so it's an error as an exception condition generate within the currently running process. Okay, so if the OS determines, so if the condition is a factor, then they will move to a exit state and their process switch occurs. Okay, so that action will depends on the nature of that error. Okay, so because for different type of error, maybe for something like for input, or like for something like a referral address memory or something else. Okay, then based on those, then we have different type of option. Also, if you remember, we have the change of process stage, right? There we talk about like 5 stage. So this is a step or like full process switch. So first we try to save the context of processor. Then next we need to update the PCB. So if you remember in the PCB, we do have the stage, right? Or the processor accounting information. Then next we will move the PCB to a queue. So those like queue including ready, block, or ready, suspend. So this one is the depends on how many stage we are using. Okay, so and then select another process for execution, dispatcher. Okay, so if you remember this part, and then next we'll move on to update the PCB of the process selected. Let's say that stage is from now, then like go move to from ready to running. Okay, and also we need to update the memory management structure. So maybe the current process VM status. Okay, so if you remember, because in the VM we talk about all the process, we assume they're thinking they own all the resources, right? So if you remember, and then we need to restore the context of select the process to CPU register. So right here, okay, over here. So if the current running process like is to be moved to another stage, let's say ready, block, etc. Okay, then the OS must make a substantial like change in its environment. So we also need to doing management of resources. This one will be later, like for more detail, when you know, then you can link all this knowledge. And after we go through all this about OS, then we need to think about what's the security issue. Okay, so what's the implications of like process and security in an OS? So the security issue associate a set of like privilege. We talk about privilege with each process. So typically when a process they execute on behalf of a user, right, in a user mode, and we have the privilege that the OS recognize that it's for the user. The highest level of privilege may be referred to as an administrator, supervisor, or root access. So for Windows, we have the root account supervisor. Sometimes for Linux, we have the root, right? So we have the highest privilege right to do it. And the key security issue is that designed for any OS. So it's to prevent or at least detect, or we can attempt by a user or a malware program from gaining unauthorized privilege on the system and from getting a root access. So here's all the targets when you're learning cybersecurity. Okay, we do talk about that. And of course, there are two ways for the intrusion. Then we have intruders or the malicious software. Okay, so right here, the objective is that they want to gain the access to system or increase the range of privilege accessible on the system intruder. So because they try to hacking, right? Hack your system and attempt to accrue information that should have been protected. Here's the access friend. Okay, for those malicious software. Okay, so most of the sophisticated type of the twist to those to the computer system. Okay, so can be relatively harmless or very damaged. So it really depends on those malicious software they want to do. So how can we have some encounter measures for those intrusion detection? So security service. So we need to monitor and analyze the system event for the purpose of finding, provide some real-time or near real-time warning of, and attempt to access system resources in an unauthorized manner like this, or maybe host or network-based, it can be. Or the intrusion detection system, IDS. Okay, covers 3 logical components, including maybe sensor. Okay, how can we have using sensor? Okay, and then analyze them and then provide the user interface. So the IDSs, so they are typically designed to detect human intruders behavior as well as the malicious software behavior. So here's the idea. This is pretty long time ago, but if you look at your Windows, maybe a Defender, so maybe we do have some pretty similar idea. And also the authentication. Okay, so right here, the process of verifying an identity, okay, can by or for system identity. So consists two steps. One is the identification, one is verification. So that's what we need to do. One is we need to know identify who you are. Okay, may verify. Okay, checking. So is it matched? Okay, there's some general mean of authentication of user identity. So something that the user know or what the user owns. Okay, maybe some something like the user is something maybe a biometric. Okay, right, or what they need is a dynamic biometric. So all this can be identifying for the authentication. Okay. And then next is the access control. So if we need to implement a security policy that specific who or what may have access to each specific system resources, and also the type of access that is permit in each instance. So maybe have a mandate between a user or system resources, and also the security administrator maintain an authorization database. And also we can add the auditing function monitor to keep a record of user access. So we are logging, okay, so which user access to which directory folder, okay. So here kind of way for access control. And last one, here we'll talk about the Unix process management. So it's the implementation of process stage and management in real OS. Okay, so more history example, they are pretty outdated, but I would say just giving you an example. Okay, quickly go through Unix as well 4. So it's the use of the mode. So most of OS execute within the environment of the user process. And then the system process, they run in a kernel mode. Okay, they execute the OS code to perform an administrative or housekeeping function. This is basic. For the user process, you're going to operate in the user mode, execute the user program and utilities, and operate in the kernel mode to execute some instruction that belongs to the kernel. So you see they are separate. And enter kernel mode by issuing a system call. So if you remember with the system call system function, so when exception is generated. So when an interrupt occurs. So right here, imagine where we say the system mode and then the user mode. Okay, we do have a system call. And right here also that belongs to the process stage. Um, right here belongs the Unix. Okay, so we have a user running, executing user mode, kernel running, executing kernel mode, ready to run in memory. So those like I'm ready to run as soon the kernel schedule it. So they're putting the ready to run. Asleep in memory, unable to execute until an event occur. So it's a processor in the main memory. So kind of like we can treat it as a called block state. Okay, we are waiting for event. So if you see asleep and ready to run, swap. So if they're ready to run, but the swapper must like swap the process into main memory before the kernel can schedule it to run or execute, we say, then it's called ready to run. And sleeping, swap. Okay, so if the process is waiting an event. If you remember, sometimes like for a state, we talk about waiting for event. So they swap to the second storage. So it's kind of similar to our suspect, right? And also a preempt. So if the process is returned from kernel to user mode, but the kernel like preempted, and does the process switch to schedule another process? So this one, and then we have create. So this one is newly created and not yet ready to run. Okay, so if we remember we have the new stage that kind of similar to create, and then we have the zombie. So it's no longer exist, but it leave a record for its parent process to collect. So if we remember, sometimes we have the parent process and then we create the child process. Okay, so here's the all the stage. If you look at the graph, so right here, so start the beginning. Sometimes here you can see we have the fork function. Okay, so that's how we create a new process. Okay, so once we create, then we have the ready to run. So like ready to run in the memory. Okay, if we need to check, do they have enough memory? Yes, in the memory. If not, okay, then maybe swap. Okay, so we will swap in and out between these two stages, and then we will, if we're ready, so we will move on to the kernel running, so we can schedule it. So later, if we are able, then we can return it to the user running, and then and if we can say we have preempted, then we have preempted right here, and then we can return to the user. If we finish, we have some like system call interrupt, then we can go back to the kernel running. Okay, right here in between, if itself kernel, we also have an interrupt return. Okay, if we still exist, then we have the zombie. So it exists right here. So waiting for the parent process to be called back. And in case we need to like suspend or somehow we put it to sleep. Okay, so sleep memory, swap out. Okay, go to sleep, swap this right here. And maybe we need to put it back, ready to run. Okay, so it's a pretty similar. So we do have a different states for Windows or for the Unix. This one maybe for the Linux. So all this we have different way showing. And for a Unix process, okay, so right here, including we have different name, but it's pretty similar. We have the process text, data, user stack, and then share memory. So right here, the text is a machine instruction of program data accessible by the program. And then also for the user stack, all those are argument, local variables, pointers, or function. Okay, and share memory, so they share other process. And we do have a register context, right? So we still need the context, including the PC, okay, and process state status register, step pointer, general purpose register registers. So all this will be the address of the next instruction for the PC. That's what we learned see before, and then the processor status register, it contains the hardware status and the time preemption, okay. Also, the stack pointer point to the top of the kernel or user stack. So it really depends on the operation at the time preemption, okay. And also a hardware dependence for the general purpose register. And also we have some system level context, including process table entry, user area, like the preprocess region table, kernel stack, so all this. We don't have to check all these details, but if you're interested, you can look at it. And there's one more table, so it just like explaining what's the process status. Okay, so if you remember, we have the different type of table, right? For when we talk, but that one is more like closer to Windows. But for Unix, we do have a process table. So including the process status, pointers, like those like maybe point to like some area or process and memory. Okay, so those that we call the text data stack. Also the process size, and also the user identifier. So those are view user ID. Okay, or some like effective user ID. They may be used like by a process to gain the temporary privilege, right? And also we have the process identifier. So the ID of this process and the event descriptor. So it's rated when a process is in a sleeping state, because we do have the sleeping stage right here. And we have the priority, so using for scheduling signals, numerate the signals to send the process that are not yet handled. We do have the timer. So what's the process execute time, the p-link pointer to the next link. Also the memory status, so indicate whether this process image is in the main memory or swap out. So here's all this. You see, maybe the naming or some of them, they are not exactly same, but so far they're pretty similar to the Windows one. Okay. And we have the process creation, including like the creation by using kernel system. Later we have the core and fork. So this one is like cause the OS in the kernel mode. Okay. And after we have a creation, so we create the process at the kernel also can do one of the following. So it's kind of part of that dispatcher routine. Either we can stay in the parent process, we can transfer to the child process, or transfer control to another process. So so far we have three different dispatcher routine we can do. Stay on the parent one, or after we create the child, okay, so we can switch to the child, or we can switch the control to another process. So either way. So far, quickly, let's summarize what we talk about the basic and fundamental concept of the modern OS. Even say it's modern, okay, but actually it's really a long time ago, okay. And also this like principal function of OS, including like how can we create, manage it in some like terminated process. So we have different states. And we always like emphasize one is the PCB, the control process control block. So it connect all the information. So that is required for the OS to manage the process, including the current stage that we care about, resource allocate to it, priority for scheduling other relevant data. Most important is like we need to know the state, including ready. Okay, so they're ready, and then sometimes we have the ready queue. Okay, running. Okay, if we waiting for event, we need to put into block. Okay, and if the running process like that one is currently being executed by the processor, you need to know. And the block process is waiting for the completion of some event. Okay, so once we have the event occurs, then we can put it back to ready. Okay, and also a running process is the interrupt either by the interrupt or by executing a supervisor code to the OS. So remember we talked about interrupt too, so we need to remember. So far, we quickly cover all this part related to process, and thank you so much.